And welcome back! Today we discuss a very versatile algorithm, the depth-first search. The depth-first search describes a method of searching, usually on graphs, but we're going to start by looking at a real-world example. So let's get started. Imagine you were in this maze in the room at the very top. What could be a strategy for certainly finding the exit? The depth-first search strategy could be described as always take the leftmost path that is unvisited, and if there is no unvisited path, go back. So in our example, we start here, and then at this intersection we choose the left path. We follow the corridor, and at the intersection we again take the left path. Oh, that's a blind end. So we go one step back. At this intersection we already have visited the left path, so we take the right one. Again a blind end, so back again. Now there are no other paths left, and we go back yet again. Here we already have visited the left path, so we take the down path. Nope, so we take the right one. Continue straight, then take the left one, and we're out! With this strategy you can escape every maze. Now, in computer science we like graphs. So let's represent our maze with a graph. Now, rearrange it. That looks a lot better. Our algorithm starts at node A and then visits one of its unvisited children. This can be the leftmost or the first in alphabetical order. In the end, it does only matter that it is unvisited. So the next node could be B, then E, then back up to B, then F, and then all the way back up to A, and so on. We first go into the depth of the tree, then back up. So that's why we call it depth-first search. Now let's see how we can implement the depth-first search. Meanwhile, we have a look at a different example. This graph is not a tree like the one before, but contains cycles. But we will see that that's not a problem at all. We start by setting a visited flag for all nodes to false. Then we have a method called DFS of node U. This means that we begin with our search at node U. So we set our visited flag to true for node U. Then we check for every neighbor node V if it is unvisited. If it is unvisited, we recursively call the depth-first search for V. Let's see that in action. We start with DFS A. Then we set A to be visited, then we visit B. We iterate over all neighbors of B, but A is already visited, so we choose D. All of these neighbors are visited, so we do not perform a recursive call and continue at B. B's only unvisited neighbor now is E, so that's our next node. Then we continue with F, G and C. Now all of C's neighbors are visited, so we return to G, F, E, B and A. That's it! If implemented with adjacency lists, the algorithm runs in O of V plus E, as we need to iterate over every vertex once and over every edge at most twice. You may be thinking, wow, now I can solve mazes. How useful! But wait, the depth-first search is extremely versatile and can be used for many problems. For example, we just converted this cyclic graph to an acyclic graph if we only take the edges we visited. Or it can be used to test if the graph is fully connected. If you want to try implementing the depth-first search yourself, I'll leave a link to a competitive programming task in the description where you need to check if a graph is connected. Today we learned a technique of traversing a graph efficiently. This can be applied to a variety of problems, like checking for connectivity, and many more. Be sure to try it out yourself, and I better see you in my next video.